Assalamualaikum warahmatullahi wabarakatuh, and a very good morning everyone. So today we continue our lesson on Digital Electronics Chapter 6 Combinational MSI, and today is the last part of Chapter 6, which is concerning about adders and comparator. So at the end of today's lesson, you will be expected to know what is the function and how to operate the adders and comparator, and you will also know how to design the adders and comparator circuit. So without further ado, let's continue. So the first part of our lesson is about adders. So what is actually adders? So adders combine two operand arithmetically using binary addition rules. So basically, adders it is a type of combinational MSI which is used to perform binary addition. So in adders, there are three types of adders. So the first type is the half adder, the second type is the full adder, and the third type is the ripple carry adder. So to know what is the function and how to operate each and every type of adder, let's continue. So right now you will learn about half adder. So half adder accepts two binary digits on its input and produces two binary digits on its output, which is sum bits and also the carry bit. So this is the logic symbol of half adder, which is consists of two input, which is A and B, and two output, which is the sum and also the output carry. Okay, to know how the half adder operate, let's take a look at the truth table of the half adder. So this is the truth table for half adder, which is consists of the inputs and also the outputs. So basically, half adder it is used to operate the addition of two different variables altogether. So it means that A plus B will be producing two output. So each output has one bit of output. Okay, so let's take a look at the first row of the truth table. So the first row is 0 plus 0. So when you are doing the what we call binary addition, the output will be 0. So at the sum, it will become 0, and there is no carry at the half adder. Okay, next, when A is equal to 0 and B is equals to 1, so it means that 0 plus 1 will be equals to 1. So right now, the output still consists of 1 bit size. So it will directly goes to the sum. So sum equals to 1 and there is no carry. So carry will be equal to 0. So next is when A is equals to 1 and B is equals to 0. So 1 plus 0, it will be equals to 1. So still, the output doesn't have to be in 2 bits. So 1 will be goes directly to the sum and there is no carry. So the carry out will be 0. And lastly, when A equals to 1 and B equals to 1, when you perform the binary addition, you will get an output of 1, 0. So this time, you will see the output must be in 2 bits size, which is 1 and 0. So it means that the LSB part, which is the 0, need to go to the sum, and the MSB part of the number will goes to the carry. So the output will become 1, 0. Okay. So from the operation of half adder, we can derive that. So from the operation that I've been shown you previously, we can get the equations of C out and also the sum. Okay. So to get the equation of the carry out, we can just simply use the SOP expression when we are observing the output of 1 and we take a look at the input. So when the output is equals to 1 A is equals to 1 and B is equals to 1, it means that the Cout equals to A multiplied by B. Okay, next we will figure out the equations of the sum. So sum will be equals to A B bar plus A bar with B, and it will be the XOR operation. It will become XOR operation. So to get this expression, we are using the same procedure when we observe the output situation when the sum is equals to 1. So when the sum is equals to 1, A is equals to 1 and B is equals to 0, it what I call represent A B bar. And the second part, when sum is equals to 1, is when A is equals to 0 and B is equals to 1, A bar and B. So from this operation, we can figure out what is the logic gate of the half adder. So this is the logic gate of the half adder. This is the A and this is the B. So for the carry out, we can just simply multiply it together by using AND gate. And for the sum, as this expression represents the XOR operation, it will become XOR gate. We can just use the XOR gate to perform the sum operation. Okay. Next is full adder. So full adder accepts two input bits and input carry, and it will generate sum output and output carry. So previously you learned about half adder. So half adder consists of two inputs, which is A and B. But this time, full adder consists of three inputs, which is A, B, and also the input carry. So right now, we have three inputs for full adder. And the number of outputs is still the same, which is we have the sum and we have carry. To know how to operate the full adder, let's take a look at the truth table. So this is the truth table for full adder. So as you can see here, the input number has been increased into 3 with an additional of Cin inside the input. So as you can see from the previous example of the half adder, so half adder operate the addition operation of A plus B. But this time, the full adder will show the operation of A plus B plus Cin. So in order for you to show some example on how to operate the full adder, I will show you 3 different examples. So the first example is when A is equals to 0, B is equals to 0, and Cin equals to 0. So 0 plus 0 plus 0, it will be equals to 0. So as you can see here, the output is in 1 bit only. So it will goes directly to the sum and no carry is produced. So next is when A is equals to 0, B is equals to 0, and Cin is equals to 1. So the output will become 1 because 0 plus 0 plus 1 equals to 1. So this time, the output also have only 1 bit. So it means that it will goes directly to the sum and no carry will be produced. So the last example is when A is equals to 1, B is equals to 1, and Cin is equals to 1. So you know that 1 plus 1 will become 1, 0. Then 1, 0 plus 1, it will become 1, 1. So right now, your output of addition will become 2 bits. So the LSB part will go to the sum and MSB part will goes to the output carry. Okay, so next I will show you how to get the expression for sum and output carry. So from the operation of full adder, we can derive Boolean equations of Cout and sum by using K-map. So because the input variable has been increased into 3. So it is quite complicated for us to get the Boolean expression by directly using the truth table. So we need to use the cutoff map. So this is the K map which is produced for Cout, which is the output carry. So here you can see that we have the first group. So the first group has the expression of A and B. So this is the second group. So the second group has the expression of C in A. And last group, you see that this group has the expression of C in and B. Okay, so you will get the expression of the Cout, which is C in B plus C in A plus AB. And this is the K-map for sum. So you see here, for K-map, when we want to derive the expression of sum, we have 4 different expressions. So the first expression is the C in bar, A bar with B. And the second expression is C in AB. The third expression is the C in A bar with B bar. And the fourth expression is C in A. So you can get the expression of the sum, which is C in A bar with B plus C in AB plus C in bar A bar B and plus C in bar A B bar. So from this expression, we can further simplify into C in A bar with B bar plus AB plus C in bar A bar with B plus A B bar. And then you can further simplify, and finally you can get the expression of C in XOR A XOR B. Now, after you get the expression of Cout and the sum, you can get the logic circuit for the full adder. So for the logic circuit for full adder, it has a total of 2 XOR gate, 3 AND gate, and 1 OR gate. So to get the expression, we combine A and B into XOR gate, we get A XOR B, and then C in will be directly connected to the second XOR gate. So the output that you will get is the equation of the sum. So sum equals to C in XOR with A XOR B. Okay, the next expression that you will get is, you will get A, B, and then the second expression you will get is A, C in, and then the last expression that you will get is C in B. And then you add it together, you will get the expression for the Cout. Okay, the output carry, you will get C in B plus C in A plus AB. So this is the general logic circuit for the full adder based on the equations that we get from the K-map that we have drawn in the previous slide. Okay, next is how to design a full adder using half adder. So for your information, we are also able to design a full adder circuit by using a half adder, circuits. So this example shows how you can design the full adder by using 2 different half adder. So we have half adder 1 and we have half adder 2. So as we have learned previously, half adder has a total of 2 input, which is A and B. But full adder has a total of 3 inputs, which is A, B, and C in. And in order for you to design the full adder by using half adder, the first 2 input, which is A and B, will be directly connected to the first half adder. And then the sum from the first half adder will be connected to the input A of the second half adder. And then we have the third input, which is the C in for the full adder, because we have 3 inputs. So C in will be connected to the input B of the second half adder, and then the carry output carry for the first half adder will be connected to extra gate. So for this example, we are using OR gate. So it will be connected to the OR gate, and then for the full adder, the number of output is similar with half adder. So the sum of the second half adder is equals to the sum of the full adder that we are designed inside this circuit. And the output from the OR gate, which is the combination between the output carry of half adder 2 and also output carry of the first half adder, will be adding together, and we can produce the output carry for the full adder. So this is the what we can see inside the half adder, which is XOR gate and also the AND gate. Okay, so when we are combined all together, you can get the expression of S equals to C in XOR A XOR B, which is similar to the expression that we can get from the full adder. And also the C out will be equals to C in B plus C in A plus AB. So C in out, which is come from here. Okay, so the C out that you will get is also similar to the C out that you get from the full adder. So this is how you can design a full adder circuit by using two different half adder. So what is actually a ripple carry adder? So ripple carry adder, it is used to add multiple bit binary numbers. So as you can see from the previous lesson, you see that for half adder and full adder, the input variable of A and B only consists of 1 bit size input only. But what ripple carry adder do is, it can enable a multiple size of bit. So for ripple carry adder, the size of A will become 4 bits, and the size of variable B will also become 4 bits. So it will enable a multiple bit binary number addition operation. So the carry out output from a state is connected to the carry in input of the next state. So for this statement, in order for us to design the ripple carry adder, we need 4 full adders. So for 4-bit ripple carry adder, we need 4 full adders. So for each and every full adders, the carry out output will be connected to the carry in input of the next state. So for ripple carry adder, we have an input of A3, A2, A1 and A0 with each and every variables represent 1 bit, and B3, B2, B1 and B0 with each variable represent 1 bit. So it has a total of 1, 2, 3, 4 bit for variable B, and 1, 2, 3, 4 bit for variable A. And we also have the CO. So the CO is the initial carry. So initial carry is initially set to 0 because we don't have any carry at the initial state of addition. So the output from the ripple carry adder, we have a total of 4 bits of output, which represent by S3, S2, S1 and S0, and also the C4. So C4 is the output carry for the ripple carry adder. Now let's take a look at the example given for the question of ripple carry adder. So in this example, I will show you how to operate the ripple carry adder, which is the addition operation of 4 bits of binary number. So this question given as 1001 plus 0101. So when you get this question, you can divide this question into 2 different sections, which is 1001 into section A and 0101 into section B. So this is the logic diagram for the ripple carry adder, which is consists of 4 different full adder. So this is the categorization that I've been mentioned to you before. So the first 4 bits of the number, which is 1001, so the what we call the MSB part of the number will represent A3, and the LSB part of the number will represent A0. So for the second category, the MSB part will represent B3, and the LSB part will represent B0. So you see here, this is the conventional addition operation that we can see for the binary number, which consists of the carries, input A, input B, and also the sums. Okay, so how to solve this problem? First, we need to initialize the initial carry, which is connected to the full adder 1. So initial carry will be initialized as 0 because there is no carry at the initial state of the addition. And then 0 will be connected to the Cin. So after that, we add 0 plus 1 plus 1, it will be equals to 1, 0, where 0 will go to the sum, and then 1 will goes to the carry. So for the first full adder, 1 plus 1 plus 0 will be equals to 0, and the carry will become 1. So 1 will be directly connected to the second Cin, and the second, what we call input, which is B1 and A1, which is 0, 0. So 1 plus 0 plus 0 will be equals to 1 with the carry of 0. Okay, so you get 1 with the carry of 0. So 0 will be connected directly to the Cin of the third full adder. Okay, so the input A2 and B2, which is connected to the full adder 3, which is 0 and 1. So we add it together, 0 plus 1 plus 0. So you will get the answer of 1 with the carry 0. So you get the answer 1 with the output carry of 0. So output carry will be directly connected to the last input carry of full adder number 4, and it will be adding together with the last part, which is the MSB of the input, which is 1 and 0. So 1 plus 0 plus 0 will be equals to 1 with the carries 0. And then you will get the sum of 1 and the output carry of 0. So from this operation, you will get the final answer of 1, 1, 1, 0, which is consists of 4 bits of output. Okay, so this is how the ripple carry adder operate, where first you need to initialize the initial carry to 0, and then you connect the what we call the input A and B of each and every full adder correctly, where it starts from the LSB part of the input and it ends with the MSB part of the input A and input B. And then you just do what we call a conventional binary addition, 1 plus 1 plus Cin, and then you will get the sum and you will get the carry, and then the carry out will be bring into the second full adder carry in, and then it will be repeated and repeated, and you will get the final answer, which consists of 4 bits of sum and 1 bit of carry. So next is the IC of ripple carry adder. So for ripple carry adder, we are using 74x83. So this is an example of IC device for a faster 4-bit ripple carry adder. So this is the logic symbol of 74x83 ripple carry adder, which consists of the first operand, which is A, the second operand, which is B. So you see here, you have the A1, A2, A3, and A4, and B1, B2, B3, and B4, which is 4 bits of each and every operand. Okay, so this is the 1 bit input carry, which is the initial carry. That usually initialized as 0 because there is no carry at the initial state of addition. And you will have a total of 4 bits of sum and 1 bit of output carry. So actually the circuit that you see, what we call the 4 full adder, is located inside this IC. Okay, so you see here, this is the conventional addition which starts from A4. So A4 here is the MSB part of the operand A, and A1 is the LSB. So you need to know which pins need to connect with which type of number, so that you will not have the wrong circuit connected to the 74X83 ripple carry adder IC. Now, let's take a look at the second example. So this is the second example. So figure below shows the block diagram of a 2 bits adder A2, A1 and B2, B1 addition. So the result should be in 3 bits binary number C2, S2 and S1. Obtain the truth table for output C2, S2 and S1. So in this question, the question asks you to find the truth table for output C2, S2 and S1. So it means that you have a total of 3 different outputs. So in terms of inputs, you will have a total of 4 inputs, which are B2, B1 and also A2 and A1. So the figure given is a 2-bit adder because you need to compute the 2-bit adding operation. So in 2-bit adder, this is the conventional methods of adding the binary number, which A2 is the MSB, A1 is the LSB, and add with B2 and B1, and you will produce a total of 3 output, S1, S2 and C2. So in order for you to compute the addition operation, you need an extra carry, because when A1 plus B1, you will produce 1 sum and also 1 carry. So let's take a look at the answer for this question. So this is the answer for the example 2. So as you see here, you will have a total of 16 truth table rows because you have 4 total inputs. So 4 total inputs to the power of 4 equals to 16. And that's why you have a total of 16 possibilities for all input. So how do we obtain the truth table for the output? So in order for you to obtain the truth table for the output, you need to use the conventional method of binary addition. For example, when A2 is equals to 0, A1 is equals to 1, B2 is equals to 1, and B1 is equals to 0. So it will become 0, 1 plus 1, 0. So when we compute the binary addition, 1 plus 0 equals to 1 with carry 0. And then 0 plus 0 equals to 0. 0 plus 1 will be equals to 1 with carry 0. Okay, next, when A2 is equals to 0, A1 is equals to 1, B2 is equals to 1, and B1 is equals to 1. So your addition operation will become 0, 1 plus 1, 1. So 1 plus 1 equals to 1, 0, where zeros goes to the sum and 1s goes to the carry. And then 1 plus 0 equals to 1, and then 1 plus 1 equals to 1, 0, when 0 goes to the sum and 1 goes to the carry. So the answer that you will get the answer of 1, 0, 0. So you repeat the same procedure for each and every possibilities inside the truth table. So at the end of the operation, you will get the answer for each and every output. So you just do the similar, what we call, adding operation, and you need to make sure the sequence of the digits. When A2 is the MSB, A1 is the LSB, B2 is the MSB, B1 is the LSB. So by referring to that reference, you will be able to compute this truth table. Okay, now let's take a look at the second section of example 2. So in this example, design the adder using 3 half adder and logic gate by completing the figure as follows. So this question asks you to design the 2-bit adder that you have done in the previous section of question by using 3 different half adder. So how to solve the problem? Let's go to the next slide. So in order for you to solve the problem, you need to go back into the conventional method of binary addition, where A2 A1 plus B2 B1, which is 2-bit addition. So in order for us to solve the addition operation, you need to solve at the LSB part first, the least significant bit, where A1 plus B1, it will produce S1, and we can what we call operate by using half adder because it has 2 input. So we can inject A1 and B1 directly to the input of the first half adder. So at the half adder, it will produce a total of 2 outputs. So the first output is S1, which is the sum, and the second output is the carry. So right now we have the carry here. So our second part of the addition operation will become a total of 3 inputs, which are C1, A2, and B2, and it will produce S2 and C2. So in your opinion, what type of adder has a total of 3 different inputs? So I'm sure you already know, right? Because half adder has 2 input, but full adder has a total of 3 inputs. So we can directly inject a total of C1, A2, and B2 directly to the full adder. So we can compute the 2 output, which are S2 and C2. So to solve this question, you need to have one half adder which is connected to A1 and B1, which is the LSB, and it will produce S1 and C1. And then because the next input, we have a total of 3 input, C1, A2, and B2, we need to use full adder because full adder provide the operation for 3 input addition. Therefore, you can directly connect C1, A2, and also B2 inside the full adder, and you will produce S2 and C2. So the question asks you to design the circuit by using 3 half adder. So how you wanted to design the circuit into 1 half adder and 1 full adder? So let's take a look at the final answer of the question. So this is the final answer of the example 2 part B. So for the answer, you have a total of 3 half adder. You have half adder 1, you have half adder 2, and you have half adder 3. So based on the previous idea on how to solve this problem, you need to have 1 half adder and 1 full adder. So before we proceed on how to design a full adder by using 2 half adder, let's take a look on the procedure to solve this problem. So first, you need to solve this problem by what you call solving the addition operation of the LSB part, which is A1 plus B1, and you will get S1 and also carry 1. So A1 and B1, you can directly connect it to the first half adder 1. So the output from the first half adder, you will get a sum. So sum will be directly connected to S1. And then you have another output that is called Cout. So Cout will become the carry, output carry for the first half adder. So right now you have 3 inputs that need to be added together. So you need a full adder because full adder can provide an addition operation of 3 different input, where half adder only provide the operation for 2 input only. Okay, so we proceed to the design of the full adder by using 2 half adder. So based on the previous slide, I already shown you the connections of each and every pins that needs to be connected in order to design a full adder by using 2 half adder. So for the design, you need to have another logic gate, which is OR gate. So the first step of connecting the, what we call these equations, this expression into the full adder is you need to connect A2 and B2 to the second half adder. And after that, you need to connect the sum into the input of the half adder tree. So right now, the input of half adder tree, you already have A plus B. So right now, you need another input, which is C1, which comes from the C out. So C out will connect it to the A. So right now, half adder tree has the input of A2 plus B2, which is A2 plus B2, the output sum, and then connected to another input, which is C1. So for half adder tree, you already have C1 plus A2 plus B2. So the answer that you get from the half adder tree is the sum. So the sum represents S2. And another part of the output of half adder tree is the carry, what we call output carry. So based on the connection of designing one full adder by using 2 half adder, you need to connect each and every output carry of half adder 2 and half adder 3 into the OR gate, so that you will get the expression for C2. So this is how you can design a 2-bit adder by using 3 different half adder. So the idea is by using 1 half adder and 1 full adder.